Hello, in this video we go over Cramer's rule. All right, so Cramer's rule is used to solve systems of linear equations. So suppose we have a system of linear equations and I'm going to write a general form and I'm only going to use two variables. Suppose I have ax plus by equals u, cx plus dy equals v. The system can be written as a matrix equation ax equals b, where, all right, so let me make that more clear, where I have A, B, C, D, and this is the matrix A, and then I have the vector xy, column vector xy, and that's x gives it a vector, unknown vector, and then I'll have uv, and that's what I'm calling b. All right. So I feel like for some reason I just didn't allow myself enough space. I'm going to move all this stuff down to here. We have an example. I'm going to move that first. Okay, so that's in itself something to study, is that we can express a system as a matrix equation. A unique solution, let me just say it this way. If a unique solution exists, then it is given by the following. Okay, so our solution would be x equals a number, y equals a number. And so it turns out that it can be written in terms of determinants. It can be written as a fraction where the denominator of the fraction is the determinant of this matrix A, B, C, D. It's the coefficient matrix, or the matrix of coefficients. So you have the determinant of that. You take the determinant, put that in the denominator. That's part of our solution. The numerator is what I'm going to call the determinant of the matrix AX. So let's be explicit what A and AX are. Okay, so A we already know that I wrote down there. Okay, so what is AX? So this is the big thing in Kramer's rule, is that you take the matrix A. So here's A right here. You take the matrix A and you replace the first column. When I'm finding X, you replace the first column, which I'm calling the X column, because here we have AX, CX, and here we have AC as our column vector. You replace AC by this vector B. And so this gives UV, and then we keep the other one the same. Okay, so this guy here, let me use some different color. This guy right here, this one right here, too bright maybe. Okay, let's use this color. Okay, so you take that vector on the right, and then you replace that in the first column, which is the column that corresponds to our first unknown. In this case, I labeled it X. Okay, and then you find those determinants, so that these vertical lines mean determinant. So then Y is given by something similar, where in the denominator I have the determinant of A and then the numerator AY. Now, if you went to a different book, they might not call this AY, they might call it A2 and AX, A1, or I mean, there's different ways to say that, but again, the vertical lines mean determinant. And so an A will stay the same. And in the numerator, I write down the matrix A, but in the second column, which I'm saying is the Y column because that second column corresponds to the variable Y. So I have, B and D. That's B and, that's BD here. I'm going to replace that by these UV, by the matrix on the column vector on the right. The proof is actually, it uses properties to determine to prove this. Now this is only a 2 by 2 case. However, this same thing applies for 3 by 3. What I mean by 3 by 3, I mean if I had 3 unknowns, here I only have 2 unknowns, and if I had 3 equations, then I can use Kramer's rule for 3 unknowns and 3 linear equations. And it's the same idea. For x, you replace the first column by this matrix, or by this vector B. For y, the second column by B. And then you have z, well, you replace the third column by z. And what do I mean by replace? I mean taking your matrix of coefficients, the matrix of coefficients is just lifted from these guys there, those entries, or those coefficients. And you replace the first column by UV for x, the second column by UV for y, and if it's a 3 by 3, there's a third column, and you replace the third column by this vector here. Okay, so that's Kramer's rule. Okay, so let's go ahead and actually solve a problem. And the reason I'm doing 2 by 2 is for the reason it's just easier to find the determinant of a 2 by 2 matrix. All right, so this is A, X equals B. All right, so this vector on the right here is B. And so we have that X is equal to, or X, the vector X is given by XY. All right, so I'm going to start off with X. X will be given by the determinant of AX divided by the determinant of AY. Why do I write the word determinant just to make everybody make it clear that that's what I'm doing? There's just 2 different ways, or there's probably more, I think there's more, to express determinant. But so that's determinant. Okay, and so what I mean by that is that I'm going to, well, let me first do the denominator, the determinant of A, where I have 1, 2, 3, 4. So that's A. And now I'm going to copy down A, except in the first in the first column, I'm going to put in 1, -1, which is B. Okay, now let's also recall how to find the determinant of a 2 by 2 matrix. So the determinant of A, B, C, D is given by AD minus BC. All right, so it's a fairly simple formula. So therefore, let me put a box around this first. And let's just put like little snail tracks leading down to here. Okay, so therefore this is equal to, let's start with the numerator. So I'm going to multiply across the diagonal. So let me make it clear, at least clearer, what this formula is. You take the A and the D, that's AD, and then you subtract B and C. So you go first across the main diagonal, and then you go the other way with the subtraction. All right, so for our case, we have 1 times 4, and then we'll subtract -1 times 2. So we have 1 times 4 subtract negative 1 times 2. And I don't know. Okay, the question is how many little steps here? Okay, that's 4 plus 2, which is 6 in the numerator. And then for our denominator, we have 1 times 4 minus 3 times 2. So that gives 4 minus 6, and that's negative 2. And looks like we're almost there. So that's negative 3. In other words, x equals negative 3. So, I mean, this was quick because it's only 2 by 2 determinants. And, okay, so I hope that's clear that also that this is going down leading to here. So I just had a little detour around my note. All right, and then y is equal to the determinant of ay over determinant a. And so again, a different book might label that matrix in the numerator different, different letters, so, but it's all the same. And the determinant A is again the same thing. It's our matrix of coefficients there. And then AY is that same matrix of coefficients. I just copied the first column exactly the same, but then for the second column we're going to use B, and I'll even highlight it in that same green, so that's the same B right there, and I'll put 1, negative 1, and then I'll use the definition of determinant where I multiply across the main diagonal, subtract the other, and then I have 1, negative 1 minus 3 times 1 in the numerator, and then in the denominator 1 times 4 minus 2 times 3. So therefore y is equal to negative 1 minus 3 in the numerator, that's negative 4. In the denominator, 4 minus 6, which is negative 2, which is 2. So we have x, y, the vector, is equal to x is negative 3, y is 2. And then also, it's a really good idea to just go ahead and check. You take this 1, 2, 3, 4, multiply by negative 3, 2, and then you get 1, negative 1. So, by the way, the matrix equation corresponds to the system. All right, I just wanted to point this out, and maybe I should even start this problem. I started off this problem as a matrix equation. So I have this matrix equation where I have 1, 2, 3, 4, x, y, 1, negative 1. I just want to point out that that's the same thing as 1 times x plus 2 times y equals 1. All right, so see what I have here? I have 1 times x plus 2 times y equals 1. And then 3x plus 4y equals negative 1. So it's so small. I should have done this maybe above here. So it's 3 times x plus 4 times y equals negative 1. Yeah, that was too small, but I was writing. So maybe just, I don't know, maybe I'll put it over here. This is 1 times x plus 2 times y equals 1. 3 times x plus 4 times y equals negative 1. And so color coding this is 1, negative 1, and then these 1, 2, 3, 4 are these coefficients here. And then our unknowns are different colors, I suppose. X and Y are, like that. Okay, so, And then I wanted to just point out that this how this could be done for 3x3 matrices. So let's do another example where we have 3x3 matrices. Okay, I'm not going to solve the whole thing. The system, all right, so let me just put something down here. X plus 2y minus z equals 0. 3x minus y plus z equals 3. And actually, sorry, I let me change this. Make that 2. Okay, I just want, okay, anyway, so then x plus 2y plus 5z equals 8. All right. Has solution given by, well, before I write that, let's go ahead and write this as a matrix equation. So this can be expressed as a matrix equation. Where all I do for these matrix equations is I just pick up the, I just pick up these coefficients here to come up with the coefficient matrix. All right, so that will give me 1, 3, 1, 2, negative 1, 2, negative 1, 1, 5, times x, y, z, and this is equal to then these constants on the right. By the way, I never have heard really a standard name for that matrix or that vector on the right. Some people call it like force vector or something, but anyway. Okay, so the solution is again given by x equals determinant ax over a, determinant of a. Well, what's that going to be? I'm going to just write it out, but I'm not going to do the problem because this video is already getting too long maybe. But that's going to be given by what? I'll put the denominator first is the matrix A. And let's see if I can just copy it down without, making a mistake copying it. Okay, so there's A, and then I put in the exact same entries for AX, except I replace this first column by those numbers for B. Okay, so that's how you do the determinant. The vertical bars mean determinant. And then Y is going to be a similar thing. All right, determinant this time. Well, maybe it won't. Looks inconsistent, but all right, AY over determinant of A. And that is, just copying and paste the same denominator. I literally copy and paste, and actually copying again and pasting again the numerator. You just copy and paste it, except what do I do with this column here, this Y column? See, I'm defining for Y. I replace it by B. Okay, so I'm going to replace that by B. And I'll put in 2, 3, 8 there. That's going to give the solution for Y. And by the way, this only works if the determinant of the denominator A is non-zero. And that's a theorem from calculus, or not from calculus, linear algebra, I don't know why I say calculus. From linear algebra, that the system has a unique solution if and only if the determinant of the matrix of coefficients is non-zero, because you can't divide by 0. So this determinant of the matrix coefficients should be non-zero. Okay, and then Z is similar, and you can, you copy and paste that. So A is, is the same, exactly the same thing. So we just copy and paste A. I have this duplicate function here. And then I'll just make it a little smaller so it fits in. But for Z, I delete the third column, the column that corresponds to, when finding Z, I delete the column that corresponds to the Z, negative 1, 1, 5. I delete that and put instead the coefficient, or the coefficient vector, not the constant vector, B, and I put that in there. And so that'll give the solutions. If you're interested, the solution, I believe, I just sort of did in my head, that the solution ends up being that X, Y, Z is equal to 1, 1, 1, and you can work that out. But for 3 by 3 determinants, there's a previous video of how to find the determinant of 3 by 3 matrices, how to find those 3 by 3 determinants. So it's more involved, but there is a solution, which is, I think I got it right, but that's 1, 1, 1. Okay, so well, that ends the video, and this video is on Kramer's rule. It's true we didn't work out this third problem completely because I didn't find the determinants of those 3 by 3 matrices, but go back to the previous video on this playlist about how to find 3 by 3 determinants. Okay, that's all. Thank you.